Okay, so we've got a packed session. I think we'll get going with the preliminaries, so we can get jumping straight into the actual talks. So welcome to Active Optics for 2021. The goal of this session is to present kind of an update on what's been going on in the project in terms of the Aos system, or AOS. And also to hear from people in the community who've been approaching the active optics systems in a range of different, or using a range of different methodologies. So as a reminder, we have all agreed to abide by the code of conduct associated with the meeting. If you notice any violations associated with the code of conduct, you can find the contact people on the Rubin web pages in order to report it, and we will address any of the issues that arise. The talk is going to be, all talks are recorded, and because we have a packed session, what we're going to do is we're going to leave the questions until the end. So if you can add the questions into the Slack channel or directly into the Zoom chat, then we will address them and work our way through once we get through all of the talks. For the presenters, I will give you a warning at 8 minutes, and then we will cut off at 10 minutes. So the goal of this meeting is really to do very much of a show and tell, and then we will follow up with more in detail or more in-depth presentations later on during the standard AOS meetings on Thursday for Rubin. The agenda that we have is that Bo is going to start out by giving us an overview of the status of AOS. Then Chris Subalak is going to talk about some advances in the simulation of both the full focal plane and the wavefront sensors using FOSIM. Josh Myers will give us an update on some work he's been doing on geometric modeling of donuts. Erin is going to be talking about the combination of atmosphere and wavefronts for PSF work. Nevin Kapler is going to give us some lessons learned from modeling of wavefronts with PFS. And then we're going to wrap up with Dave Thomas talking about some convolutional neural networks or deep learning approaches to wavefront sensing. I'll run the slides. So as you want me to advance, just let me know, just say next slide, and I will move along. And with that, I'm going to turn it over to Bo to talk about the overview of the AOS system. And Bo, I will give you a warning at 8 minutes.
Yeah. Okay, thank you, Andy. Good morning, everyone. So I'm going to give a quick overview of the status of the AOS on behalf of the project AOS team. Next, please. Okay. So this is a one-slide overview of the AOS control architecture. So it is an active optics system. We have curvature wavefront sensors at the four corners of the focal plane, and we control the mirror figures of M1, M3, M2, and the positioning of the M2 and the camera hexapods. So most of what we correct, that is gravitational and thermal effects, are taken care of by the lookup tables. The residues fall onto the closed loop wavefront sensing feedback mechanism. And we also have the laser tracker system, which is for coarse alignment to put the system into the capturing range of the wavefront sensors. Next slide, please. Okay, oh, go back. So, well, you always go 2 slides at a time, Andy, at least from my screen. Okay. So the lookup tables are very important to the AOS. Whoops, go back.
I think there's a lag. So let me actually go back and we'll just leave it for a second for you to.
Okay. Maybe I should say the number. 7. Go back to 7.
Okay.
Oh, wrong direction.
Is this the one?
Yeah, 7. Okay, stop at 7. M13.
You should have
okay.
it.
So each subsystem has its own lookup table. We always start from the finite element-based lookup table. For M13, they have been calibrated based on the optical testing results from the University of Arizona Mirror Lab. On the lower left, you see a optimized surface as seen under the interferometers. And the thermal system is having its fine coil units installed as we speak. So the support system is complete and waiting for its final re-verification. Next, number 8, please. Okay. So the secondary mirror was delivered to the summit. It has been undergoing preliminary functional testing where we verified its lookup table, the force repeatability, force balance systems, etc. So those are the functionalities that are key to the performance of the AOS. And on the lower left, you see how the axial actuator forces were changing while we rotated the mirror on its cart by 180 degrees and then back. Like the M1, M3, we have also done a lot of final re-verification planning. Next one, please. So similarly for the hexapods, on the left, you see the lookup tables for both the camera hexapod and the M2 hexapod based on the finite element model of the telescope structure. On the right, you see some results from what we call a endurance test, where we simulate a full night of Rubin operation and have the camera hexapod adjust its position by following the mount elevation angle. And these lookup tables will be further fine-tuned once the hexapods are on the telescope mount and we have the laser tracker system set up. Next one, please. So right now, all the AOS hardware is on the observatory 3rd floor. Right now, we are dedicating every Tuesday and Thursday to integration testing on the summit. If you attended the commissioning talk by Chuck Claver on Monday, you have seen this his version of this slide. So we do not have a completed telescope mount yet. So we use a mount simulator to simulate multiple visits and observe that all the components are looking at their own lookup tables and adjusting forces and positions accordingly. On testing the closed loop wavefront sensing, we feed some fake images to the AOS through the DM Butler and have the MT-AOS CSC process those images and send out corrections to the components. So this part is still work in progress. Next slide, please. So another area we have been putting a lot of efforts into is the closed loop AOS pipeline. The pipeline has many components, most of them are ready. We are mostly focusing on those 2 pink boxes you see on this slide. Those are the wavefront sensing, source identification, and donut deblending. Next slide, please. So this is my summary slide on the closed loop algorithm status. I'm not going to get into much detail here. You will learn more about them from other talks to be given by my colleagues, Chris and others. So I just want to say that a lot of work is being done on the AOS, and we have a team focusing on wavefront image processing, mostly on source identification and donut deblending. And we are also working on common filtering for wavefront estimation. There's also a lot of CSC work going on. We are supporting the summit hardware and software integration activities and the milestones. Meanwhile, there are quite a few very promising and fascinating alternative approaches, as we all know, which we cannot afford to include in our baseline right now because we have to deliver a working system on time and on budget. But the architecture has been designed in a way to allow the easy drop-ins of those alternative methods. Next one, please. So finally, just to highlight some recent work on image processing. On this slide, you see a simulated ComCam CCD raw image on the left, then the corresponding post-ISR image in the middle, and how the source how the source detection works for this example image. That is the end of my slides. Thank you.
Thank you, Bo. As a reminder, if you have any questions for Bo, we will follow up at the end of the presentations. And so now we're going to move over to Chris Subelak, who's going to be talking about FOSIM. And Chris, as before, just let me know when you want to advance.
Okay, so move to the next slide, please. I'm Chris Subelak. I work at UDAP as a postdoc for commissioning of the observatory. And I'm going to talk briefly about FOSIM, the status of FOSIM, a photon simulator that probably many are familiar with. So I'll just give a brief overview of how it works from the user perspective. It is a pretty complicated simulator that takes every single photon that goes through the atmosphere, simulates the atmosphere as multiple layers, then takes those photons as they hit every single surface in the optical system of your telescope. And there is multiple telescopes set up, including the Rubin Observatory. Then it takes those photons as they hit the detector, and it simulates all the complicated stuff that happens as the detectors read out the signal, including all the saturation issues and all sorts of imperfections that you might say occur in real life astronomy. So from the user perspective, we have a source catalog and physics commands that modify the physics that FOSIM uses to simulate the entire passage of photons through the system. Internally, it splits the focal plane into sensors. In case of LSST CAM, there is a little insert there showing you how many different rafts there are that are split into sensors. And then those sensors are further split into amplifiers. And FOSIM has to be aware of how they are oriented with respect to each other and what is the geometry. And from the user perspective, the output, the most important output is the FITS file for each amplifier, centroid files, and electron images, which are the same as amplifier images, but without all the electronic noise. So it's as if the CCD was perfect and ideal. Next slide, please. So again, from the user perspective, the point is to reproduce the camera. And most of my work for the past several months or maybe a year was to reproduce the camera to such a level of fidelity that in the end, the software that we use to read in data can think that it comes from the real camera. So starting with FOSIM, whether it's on the laptop or NCSA, we produce some raw images that are repackaged with FOSIM repackager. And we made certain updates to it so that not just the name of the file, but also the header structure and the geometry looks just like the real telescope in the upper right corner. So that when I read it in as a Gentry Butler repo saying that this is LSST CAM, it thinks it's LSST CAM. The only thing that distinguishes it from the actual real world camera is the controller. Next slide, please. So one of the updates that I had to make it work was that historically, the version that we've been working with had only ITL chips, which are one type of chips that are being used in the assembly of LSST CAM. But then there is another type of chips, E2V, that have a different readout direction and slightly different dimensions for the pre-scan, overscan. And this all had to be updated in one of those internal files that I mentioned in segmentation file. That was one of the updates that I did to make everything work and make FOSIM reproduce real world images. Next. And this is just to illustrate the problem of updating gain values. Initially, gain values were taken from some old measurements and predictions of what LSST cam would behave like, but then we had some further lab testing and commissioning results that were able to update those gain values, as well as readout noise. And so this raw image just highlights, Bo showed another image just a minute ago. Each amplifier has slightly different gain. So we need to know the properties of every single amplifier to correctly perform the instrument signature removal, ISR, and arrive at a nice image that all astronomers would love to behold on the right for every single exposure. Next. We also want the image to represent the geometry of the camera, so that when I take the image, it is assembled in the correct fashion. It seems trivial, but there had to be some small changes to be done with Euler angles, with orientation of corner wavefront sensors. I simulated a pattern of stars that are arranged on the sky in this pattern of letters, so that it would be quite clear for anybody who looks at the simulated image on the right-hand side, whether it is correct or not. Next slide, please. Here is a zoom to one of the corners of that image. And you can see the in focus for the main rafts, and the corner ones are out of focus. We're not simulating guiders. Those are the two blank ones. Next slide. We also tested the WCS information, making sure that whatever FOSIM records in the FITS header as WCS information can be interpreted by Butler correctly, so that when I read the Butler exposure and use the get WCS method and then use the sky to pixel array method, that's all built into the LSST science pipelines, I get the correct location of my sources. Here, the input is the array deck catalog, and we're basically asking the WCS to provide me the XY position, the XY pixel position. Okay, next slide. Using FOSIM, that's validated and polished in a way. I'm Polish, so I polished FOSIM. We simulated PS1 in a variety of different surface densities at high galactic latitude, medium galactic latitude, low galactic latitudes, Bade's window, and some ancillary locations such as Magellanic Clouds. And I put here a very tiny stamp, 1000 by 1000 pixels, just to show how drastically the sky density changes as you go from regions far away from the galactic plane towards the densest windows in the middle of the galactic plane. Next. And that's what happens when we take those regions and set them out of focus. Because the nice thing about FOSIM is that you can move the focal plane, you can move the CCDs however you like. So we can move the entire camera in and out of focus. In reality, the entire camera is in focus and only the corner wavefront sensors are out of focus. But here we're able to simulate all 189 sensors out of focus to provide multiple donuts for commissioning and validation of the AOS software. And the saving grace, as you can notice, is that as you take sources out of focus, a lot of things stop being a problem, such as galaxies stop being a problem because they are smeared out. A lot of stars that would otherwise overlap, as long as they have a difference in magnitude, more than 2 magnitudes, we can still treat them because the fainter one is so much fainter that it doesn't mess with the software. But we're working on deblending, and that's further areas of improvement to make it work even in the densest area, so that we can basically use as many donuts as possible for wavefront estimation. Okay, next slide, please.
2 minutes, Chris.
Okay, perfect. That's just the last 3 slides to show you the full focal plane. That's kind of the nice illustration of the capabilities of FOSIM. And next slide. I just zoom in to exactly the same image, and you start to see that those are actually not stars, those are donuts, because I took the entire focal plane. Can you switch to next slide? There you go. I took the entire focal plane out of focus so that you have thousands of donuts. So it's a nice image to finish my FOSIM presentation. We'll be happy to answer any questions later on. And I'll give time to the next presenter.
Thank you, Chris. Perfect timing. Again, if you have questions, just drop them in either in the chat or in the Slack channel. And now we're going to move over to Josh Myers. Who's going to be talking about some geometric modeling of donuts.
Thank you, Andy. Yeah, please, next slide. Right, so I wanted to talk about some donut forward modeling work I've been playing with. So forward modeling is a wavefront estimation technique used in DES, and we explored it some in HSC too, proved very useful. One interesting aspect for this group is that it requires only either an intra or extra focal donut. You don't actually need both. So that may be helpful for something like commissioning the Aos system in ComCamp, just as an example. You don't have to piston in between exposures. In the past, the forward model has been based on Fourier optics. Turns out that this is pretty slow for Rubin though, because of its big aperture and big donuts. It takes Fourier optics, around a second to produce one image of a donut, which means if you try and do a fit, you're looking at minutes per fit. So next slide. There is an alternative though, which is developed by Ryan Janisch in his undergraduate thesis at MIT, which is a geometric forward model. So the idea here is that there's a bijective mapping points in the focal plane and the pupil plane that's just given by the gradient of the wavefront. So if you want to know what the flux in a given pixel in the focal plane should be, all you really need to know is how big of a light bucket it is when you project that pixel into the pupil plane. So that light bucket size has two components. One is just what is the size of the square that may get distorted into a trapezoid or a rectangle, whatever. That's given by the inverse Hessian of the wavefront. The other aspect is, does the projected pixel actually land inside the footprint of M1 or the projected footprints of M2, L1, and so on. And it turns out that you can do this very fast, as long as W is a polynomial. So I've gotten this down to about 17 milliseconds per Rubin image. So next slide. So I wanted to very rapidly kind of show you in a cartoon form how this works. So on the left is an image of pixel space. You see a nice regular pixel grid. And then on the right is a map of pupil space with the outline of M1. So next slide. If you do this mapping with the gradient of the wavefront, you get you can move the mirror to pixel space, or you can move pixels into pupil space. If all you have is Z4, then this is a pretty uninteresting mapping. Next slide. If you add a wave of spherical aberration and a wave of pentafoil, though, for example, then the pixels get distorted in pupil space, and then the outline of the mirror gets distorted in pixel space. So next slide. And then if you want to know what is the flux in the pixel, you just have to look over in pupil space and figure out how big the light bucket for each pixel. So that the larger pixels in pupil space end up brighter in the final image. So next slide. Right, so there's more than just M1, of course, in LSST. We have to know about the other potential obscurations. So you can develop a model for those also, which I won't go into detail. This is what that looks like if you're at the center of the focal plane. Next slide. And if you start moving off the edge of the focal plane. If you're at the location of a wavefront sensor 1.7 degrees off axis, this is what that looks like in that case. So you have a lot more potential obscurations to do, but all the math is exactly the same. Next slide. And if you go far enough, you end up with a croissant instead of a donut. So next slide. All right, so how does that geometric model then perform? So I made some custom simulations. This is similar to what was done for DC2 using MSIM. I did add some new physics though to MSIM, including chromatic seeing and ray traced optics, including ray tracing through optics misalignments and mirror modes. These had a very simple catalog, so I just used blackbody stars with a range of photon levels and background level as given. There were no blends, so I just did one donut at a time. And then I used two different models for the seeing, just a simple Kolmogorov surface brightness profile and also a turbulent phase screen seeing model. And then I did a fit using the aforementioned model, looking at Z4 through Z30. So this is an example of that fitting process for the simple atmospheric model, the Kolmogorov model. And you can see the residual and the performance on different Zernikeys. If you go to the next slide, it's kind of fun to compare what happens when you use, did you go to the next slide, 43? Yeah, so this now is the turbulent phase screen model, but the optics are exactly the same. So you can see things move around a little bit with the more detailed physics. And then if you go to the next slide, on this image, all I did differently was I took the simulated donut and binned it 2 by 2, and then ran the same fitter on the binned image. And there's almost no difference in the performance for what Zernikeys are inferred, but it's about a factor of 2 faster. So that's nice. So let's see. So go on to the next slide. All right, so that was one donut. This here is showing, summarizing 700 donuts worth of data from 7 different realizations of the atmosphere and misaligned optics. So overall, most of the time, this method gets you within about 0.05 waves of the truth, 35 nanometers. The exceptions are in astigmatism, so Z5 and Z6 are a little harder to determine. If you go to the next slide, one potential mitigating technique is to fit multiple donuts at once. So you can go straight from a model that characterizes Zernikeys over the field of view all the way to pixels. And if you do that, it seems that you can remove some of the bias and astigmatism. So go on, next slide. Yeah, so that's the final slide. So this is a method that works on single donuts, intrafocal or extrafocal. It is a local treatment of vignetting. There's a vignetting model for every point in the field of view. It's relatively quick. It's about 2 seconds to fit. Unbinned data, if you bin 2 by 2, that goes down to about 1 second per fit. There are some drawbacks. So the main one is that this doesn't work if there's a caustic, because you have to be able to invert the focal pupil plane relationship. And I discovered that there are degeneracies between low and high numbered Zernikeys. So it's a bad idea if you try to fit only the low order stuff, because the high order stuff, not allowing that to vary means you end up with a biased result on the low order results. And then just as an aside, I skipped over this, but I think this is exactly the same wavefront geometry as present in CWFS, including the 10th order distortion correction that people may know about there. I incorporated that into this model as well. So that's it.
Thank you, Josh. There's a number of questions that are coming up in the Slack, and we'll come back to those at the end of the session. So our next talk is from Aaron Rubin, who's going to be talking about the combination of atmosphere and wavefront in terms of PSF. So Aaron, again, I'll give you an update. I'll give you a heads up at 8 minutes.
So as the title says, I'm going to talk about our work on a new kind of PSF model for dark energy survey and how it's relevant for us here at Rubin. The pictures on this title, the left is a real data donut from DES, and the right is a fit to it using some new things that I've done. I don't have time to talk about it, but if you want to ask questions about how the fit looks so good at modeling the distinctive fine spatial order structure, you can ask questions. Let's go to the next slide. So the idea of this approach to modeling the point spread function is to combine our knowledge of the optical wavefront gleaned from measurements across the focal plane with a physics-based model for point spread function that combines the optical wavefront and a model of the turbulence kernel. It can also include things like diffusion, tree rings, etc. The equations are as shown. The key point is that so it's a combination of Fraunhofer diffraction and a sheared von Karman kernel. The wavefront is a function of position on the focal plane and includes what I've written here as a reference that's measured plus a few additional terms to allow the measurements to vary. And those few additional terms correspond, in the case of dark energy survey, to the physical degrees of freedom. Explaining it in more detail would take the rest of the time. So instead of that, I'll refer you to the Davis 2016 paper for more details. And if people are beginners or haven't heard about this sort of thing before, I've got a few links, including a dark energy school I gave a few years ago that would be helpful. Let's go to the next slide. So let's look at the measurements of the wavefront. These are derived from an engineering image sequence with the full focal plane at decam out of focus. It's 100 I-band images with small dithers in between to move the stars around on the focal plane. So the left-hand column is data, and the top plot shows the focus Zernike coefficient. So the coefficient is Z4. You see lots of interesting structure in the data. The middle column is the optical ray tracing model from Zmax. And then on the right is the difference. You'll notice that the bowing of the sensors is very clearly visible, as is a small tilt across the focal plane, as well as some kind of interesting ring structure. Spherical looks extremely good, with the differences, kind of only in the details. Let's go to the next slide, where we'll look at the other low order Zernike coefficients as measured from decam. I've combined the two astigmatisms, 2 comas, and 2 trefoils into one magnitude, just to reduce the number of plots to look at. You can see that the gross features are quite similar to the model, but the fine features are significantly different. And if you look at the right-hand column, you see an interesting set of patterns across the focal plane. So obviously no optical system is going to get built exactly as designed. And these small, many of these are just 1/10 of a wave. So these are waves at 700 nanometers. So these are actually quite small differences. The optical system is performing extremely well compared to its design, but there are some significant deviations, and in some cases, they're more significant on the edge of the field. In any case, we'll use the measurement, not the model, in trying to understand the point spread function. Let's go to the next slide. Okay, so we have run this fit. So again, it's a fit to 18 parameters that using all of the data I just showed to model the PSF everywhere on the focal plane. This is one image. It's the first image of year 1 DES, so not cherry picked. The right is, these plots show second moment. So the IXX plus IYY second moment. The left column is the measurements from, I think it's about 8,000 stars from this image. The middle is the model after fitting the 18 free parameters. Might have been 16 or 18. Sometimes I try either. And the right is the difference. So you see there is some structure in the difference. It's possible that one CCD has slightly higher second moment. There are some structures that look like they go across CCDs. And then there's structures that could be due to turbulent patterns. Let's go to the next slide. And let's look at the same thing for some of the, for the other two second order moments and two third order moments to look a little more deeply at the point spread function. Okay, so the left two sets of plots are E1 and E2, IXX minus IYY, and 2 IXY. You can see there's lots of structure in the data. That's the left-hand images. That is pretty well modeled by this PSF approach. There are differences though. And again, those are interesting to look at, especially in this case, because the structure goes across CCDs, and I think is very consistent with what one might expect from the residual turbulence pattern that does not average out over these 90-second images. The right-hand sets are for two of the four third order moments that we typically look at. These are ones that are sensitive, particularly to trefoil. You can see the nice trefoil patterns, and you can see how well they're modeled. And the residuals are small if you look at the color scale, but there are turbulent patterns that affect the residuals even in third order moments. Okay, so that's a glimpse at this kind of fitting. Let's make some more conclusions. Let's go to the next slide. Okay, one comparison we can make, and now we'll finally make connection to active optics. So one comparison we can make is the value of the free parameters found in this PSF fitting approach with the equivalent physical terms from the active optics system at decam. So that's coming from donuts in out-of-focus wavefront sensors. So we can compare the focus term. So this is a global focus term. And on the that's the left-hand plot. On the x-axis is the value from the active optics system for about 500 I-band images. And on the right, on the y-axis is the result from the PSF analysis. You can see decent correlation, not perfect. And then on the right are the similar kind of plots from astigmatism. Again, you see decent correlation, again, not quite perfect. What is super interesting is that you can compare how well the active optics system did compared to the stars. What you'd really like to see is that these points, that these comparisons fall along a line, but most importantly, that 0 is the same, or that the points go through 0, 0. You can see focus is close, not perfect. Astigmatism Y, that Z5 might be off by 0.1 wave. Z6 is actually not so bad. What that allows you to do is to check that the set point of the active optics system gave you the optimal point spread function or not. So that's where the connection is between active optics and this approach to point spread function. Now, I will say these plots are from an earlier iteration of the fitting. We've made a number of analysis and fitting improvements in recent months, but have not run on these big samples yet again. So I'm hopeful this will actually improve somewhat. We'll see. Let's go to the next slide.
And 1 minute, Karen.
Okay, good. Okay, this is my last slide, comments. So first of all, engineering out of focus images are fantastically useful to study your system. The data I showed is from 100 sequential out of focus images. So, for Rubin Observatory, that can be taken in, I don't know, 20 minutes, a very short period of time. but you learn an enormous amount about how your optics is performing. The real point I want to make in this talk is how at Rubin Observatory's active optic system will the set point be determined. So that is the point to which your feedback system is pushing you. Over at Decam and Blanco, the set point would have, if we had tried to determine the set point using simulation, we would have failed in a significant way because of very significant differences in the data and simulation in the wavefront sensor donuts. So I showed you comparisons in the science sensors that were pretty good. They're much worse out at the wavefront sensors, which are on the very edge of the field. So instead, I used a procedure to stitch between the wavefront and science sensors in terms of wavefront. It's a little bit of a dicey procedure, I thought. So this analysis provides an independent and quantitative check of the set points using stars and the PSF that we actually care about. Another nice thing it does is that any discrepancies between the wavefront, this wavefront atmosphere PSF model, and the data point to additional contributions to the PSF. This is a bit preliminary, but it does look like over at Decam, we can see via this method some clear anomalous diffusion in some, but not all, the CCDs. And this kind of analysis could be used at Rubin Observatory. Certain modifications need to be made. In particular, there are more parameters that will be necessary because of the 3-mirror system and some allowance for the rotate. But otherwise, the ideas can be reused. Okay.
Thanks, Aaron. As a reminder, any questions, Aaron, if you put them in the Slack window, we will move on to Nevin Kapler from Princeton, who's going to be talking about lessons learned from, I believe, PFS. So Nevin, I'll turn it over to you and I'll give you a warning at 8 minutes.
Thank you, Andy. So Andy very graciously named this lessons for wavefronts from Subaru data. That's maybe a bit optimistic, but I do hope you'll find it interesting. And when we discuss Subaru data, I will be discussing data that we are taking with prime focus spectrograph. So as I assume that not many of you are familiar with the instrument, I will give like a 1-minute overview of the instrument. I will highlight some differences from the instruments that we have seen until now. And then, out of the slew of topics, I decided to show you some wavefront problems, similar as Aaron was showing. And then if we have time, maybe even some fine structure. So, Andy, next slide, please. So a prime focus spectrograph is a spectrograph being built and commissioned at Subaru telescope. So it will have 2,400 fibers and have a wide wavelength range from basically 360 nanometers to near infrared with quite good couple angstroms resolutions. And you can see the sketch of the instrument in the top right corner. Basically, it will be in prime focus. The light goes into the fibers. It goes through like 50 meters of fiber cable until it goes into there are 4 identical spectrographs. And each of these 4 spectrographs has 3 cameras, which take different parts of light. So blue, red, and infrared. As you can see in each of these modules, there is quite a lot of glass and optical elements. And then on the end, in the bottom right corner, you get a result which looks something like this. And what I'm showing here is how 1 fiber, 1 arc, 1 wavelength would look on our, in 2D space in our detector. And the biggest difference already you can see from when you look at photometric instrument is the width and the size of this spot, because if there was no aberrations, you would still get quite big spot because you will get the fiber top hat basically projected onto the pixel grid with a diameter of 3.6, almost 4 pixels. And then as I wrote also, soon we are starting to work on engineering observations where we will have the whole instrument with 1 module on the summit. Okay, next slide, please. So this PSF, point spread function, basically has 3 components. So in some methods, it's simpler, and some methods it's more complex than photometric PSF. The problem is, so you have telescope pupil illumination at the top, vignetting. Then there is the focal ratio degradation in the fibers, right? So focal ratio degradation just is the difference between the focal ratio of the input of the light at the input of the fiber and output of the fiber. What does that mean? That means if you are perfectly illuminating your fiber and the entrance, the light when it exits the fiber will not be uniform anymore. It will be smeared, okay? And that will actually change your point spread function. And then, of course, there is the point spread function just contributed from the camera, the same as in the photometric instrument. And so what we are hoping to achieve is that we are able to very well model our spectrographic cameras, know the focal ratio degradation, which shouldn't change that much because the fibers shouldn't move once when the instrument is running. And then we will know how much our instrument is vignetted at the top, and we will be able to model that out. Okay, next slide, please. So what we have been doing the defocused analysis, similar as Josh was mentioning, or Aaron was mentioning. And this is how I wanted to show you how different this illumination looks on our detectors. So we have, the columns are different fibers, and the rows are different wavelengths, okay? So one wonderful thing with spectrographs is that your spots are always at the same spot, at the same position. One horrible thing about the spectrograph is that the spots are always at the same position. So, you know, if you don't have an arc which you can cover, or you don't have data, you are not able to test this. You have to interpolate. And if you don't have some fibers because you are not able to get them on the optical bench, you have no information about that part of the detector. Also notice how these different columns, you can see how the illumination of different fibers is different, which will create large change. Next slide, please. And then I also just zoomed in onto one of them to show you the, the relatively complex structure inside, where you have the detector in the optical path, you have the struts holding the detector, you have the fiber slit, the slit holder, and all of these things that have to be modeled, and the illumination, this focal ratio degradation. Okay, and the next slide, please. You can see, I wanted to show you exactly this difference on 61, Andy. Yeah, so I try to show you, so these are two fibers which are right next to each other. And usually, of course, they will be overlapping, but we have been able to take the data with these fibers by, unplugging one fiber, plugging different fiber. And even though these fibers are right next to each other, you can see in the top panel how the illumination of them is different. And then at the bottom, these are actually models, because if I showed you data, the dipole, because the centering is a little bit different, would dominate. But I created these models, and when you subtract these models, you can see that this change in illumination basically, dominates, and you have to take that into account. Okay. Then next slide, please, Andy. I wanted to show you just some examples of our defocused modeling using the fast Fourier transform, the slow method that Josh has mentioned. For instance, this modeling goes to Zernike 56. And what we do, we struggle with illumination, but we know that illumination is the same. We take many images and many different defocuses, and the wavefront changes, but the illumination stays the same. We could do even better by knowing that the illumination is same in the same fiber, but we don't actually use that yet. What you can see is this fine structure residuals, which we are not able to resolve yet. Basically, you cannot go to such high Zernike's in a normal amount of time. And we are thinking of the ways to solve that. And also you can see that there are some structures which are obviously not pure, Zernike residuals, but some sort of, circular structures, which we are not exactly sure how to solve. Next slide, please. Then I wanted to show you, so when we plug this in, what this example is showing is the movement of one component, which is, this is Zernike 5, so it's oblique astigmatism, as we move through defocus, okay? So from the left, so it says in the top, like P 3.5, that's like we move the slit 3.5 millimeters, then 1 millimeter, minus 1 millimeter, minus 3.5 millimeters as we're going for focus, you can see how the Zernike components are changing rapidly. And if we go on the next slide, we of course have Zmax predictions also how our components should change. So for instance, I'm showing here two positions on the detector. So blue, 650 nanometers, that is in the blue part of one of our detectors, and 965 in the red part. And then if we go to the next slide, Andy, we can look what our results are showing, what our wavefront, how does it look? Also notice that the scaling is actually different. So if we were to show the same residuals as Aaron was showing, that would be completely different. So this is actually quite a big problem. And if you look at the images in focus look quite different than what Zmax is predicting. One of the things which is happening now, we only have one module ready now, but we have second module being built. It's being built in France. And we have some really early engineering data. And those data show better agreement with Zmax, again, very preliminary. So what we are thinking is that somewhere in the manufacturing of this first detector, there might have been some problems which might need to be solved. Okay, if we go to the next slide, I want to show you some—
1 minute, Nevin.
Excellent. So I want to show you some real sky data which have been done before commissioning. So this data has been taken with a telescope which is 4 centimeters, and it's perched at the top of the Subaru. And there are around 200 fibers. And you see here where there are dense fibers. This is how the real telescope will have fibers. And then we have some different spacings, so we can do various experiments. And if you look very carefully, you can see that some fibers have been subtracted, although I zoomed out very graciously so that you cannot actually see how badly we are doing. Having said that, on the next slide, which is in the blue, so this is a zoom in, and this is, again, in the blue, our modeling is better, probably because there are less manufacturing errors. You can see some of these fibers which we have subtracted. There are still some issues with centering, etc., but you can see how this looks actually quite good. And depending on which part of the detector we are approaching, one couple percent, 1% is the limit that we have decided is what we are hoping to achieve, but we might be even able to do much better. Okay, and the next slide is just the conclusions, and I'm happy to finish there.
Thank you, Nevin. Again, questions for Nevin in the Slack channel, and we will go to our, skip over your reserve slides. We'll go to our last talk, which is by David Thomas from Stanford, who's going to be talking about a deep neural network approach to modeling the wavefront. So, David, it's over to you, and I'll give you a notification when you hit about 8 minutes.
Great. Thank you, Andy. So what are the inputs and outputs for wavefront sensing? Next slide, please. So the input in the context for Rubin, the inputs are all the donut images and an observation from the 4 corner wavefront sensors. And so to be more explicit, we're going to take 196 by 196 pixel crops around each one of these donuts and their positions. And this set of donuts is the input. Next slide, please. And the output, which I call the global wavefront, we represent with 54 coefficients. So I'm going to describe how we define, like, where these 54 coefficients come from, and then describe, how we go from the input to the output. So next slide, please. So we use the double Zernike coefficients, or polynomials, to represent the global wavefront. And these polynomials are a simultaneous basis for both the focal and pupil planes. And if you had all of them, then you'd be able to completely characterize the optics and derive any metric for image quality. So here on the bottom, I show two double Zernikeys. So on the left are kind of the double Zernikeys and their indexes. And on the right are kind of the pupil plane and focal plane components. Now, what's interesting is if we look at these for Rubin, it turns out that like most of the aberration power is concentrated in low order focal plane modes. So next slide, please. So here we show if we truncate the focal plane Zernike coefficients, how much of the global wavefront from Rubin aberrations we'd pick up. And if we just got to 3, to index 3, we already get 90% of that power. Next slide, please. So we've come up with a method that breaks this problem going from inputs to outputs into 2 simple steps. In the first step, we train a convolutional neural network to take these donut images and predict 18 local wavefront coefficients, represented by alpha 4 through alpha 21 here. And once we have those for all the donut positions on the 4 corner wavefront sensors, then we use ordinary least squares to interpolate the 54 global wavefront coefficients. Next slide, please. So to train a convolutional neural network, we need a large training set. And so we simulated over 600,000 donut images. And each one of these images simulates the telescope in a different state. And I worked with my collaborator, Josh Myers, who also gave a talk earlier, to iterate on these simulations. And we believe that they are pretty high fidelity. So just some of the effects that they include are the brighter fatter effect, blending, chromatic scene, chromatic refraction, second kick turbulence. Next slide, please. So once we have this giant data set, we can build a convolutional neural network. And this network takes an individual donut and its position as inputs and predicts the 18 local wavefront coefficients as outputs. Next slide, please. So here are the results for this stage. So we have 6 donut images, and below them in blue, we have the truth, and in red, we have our predictions. And as we go from left to right, we see donuts that our network, and this is in the test set, by the way, donuts that our network does poorly on. And as we go towards the right, we end up with donuts our network does well on. And while there aren't really like standard benchmarks for this kind of work, I think it's fair to say that even the results on the left, like in the bottom 10%, are pretty attractive and probably comparable to alternative wavefront sensing algorithms. And as we go to the right, the performance improves a lot, right? So for the top decile of donuts, the mean squared error measured in wavelengths is 0.001. So we're getting like all the nuances of the local wavefront. Next slide, please. A cool thing about neural networks is kind of like an abstraction, is that we can also use them as humans to learn new truths about this problem. So one of the first things we looked at was, what is the neural network paying attention to? What pixels in the donuts are most important for distinguishing these local wavefront coefficients? And what we found is that the edges are where we have the pixels that are the most discriminating. And this suggests that we might be able to get most of the way there for wavefront sensing just looking at the boundaries of these donut images. Okay, next slide, please. So now we're gonna look at the second step of this. So once we have all these local wavefront estimates, so here we'll just look at those local wavefront estimates for one coefficient, alpha 4. And on the left, this circle represents the focal plane. So you can see in the 4 corners of the focal plane, the value of these estimates. And what we do here is we just interpolate a plane across the focal plane which is parameterized by the 3 corresponding global wavefront coefficients. So we repeat this independently for all the 18 local wavefront coefficients, and 18 times 3 is 54, and those are our 54 global wavefront coefficients. Pretty simple. And to test this, we took a mini survey of 500 Rubin observations and simulated all the donuts that would fall on the corner wavefront sensors in those observations. Next slide, please. So the metric we look at here is the magnitude of the global wavefront coefficients, the 54, after we've subtracted out our prediction over what they were before. And in the simulations, we kind of do have to fix some kind of perturbation range for the telescope. And the range we fix is actually pretty close probably to Rubin's expected operational range. So what this is showing is even when we're doing a pretty good job at wavefront sensing, we can still improve the residual quite a bit with this method. So here we see that on average, the global wavefront coefficients are reduced by 66%. And on every observation in the 500, we had an improvement. So that this kind of relative residual is less than 1. And also as a sanity check, we propagated the labels from each of the donuts as well. It's just a sanity check to make sure there isn't too much numerical error in our simulations and our labels, et cetera. And there we reduced the global wavefront by 94%. So it's a good sanity check. Now we can also look at more traditional metrics of image quality. So next slide, please.
2 minutes, David.
Great, thank you. So here is the PSF at the center of the focal plane. And the results are actually more extreme as you go outward radially, kind of before and after applying this correction. And I'll stress that this is just the optics component of the PSF. The atmosphere and system have larger contributions, but on particularly clear nights where there's good seeing, this component will be really important. And here we see that, particularly with the Strel ratio, the PSF is improved dramatically. So full width half max is reduced by close to 30%, and the Strel ratio is increased by like a factor of 5. Next slide, please. So in addition to solid performance, this approach also has nice properties. It's simple. There are only 2 steps. It's fairly robust. If we double the amount of uncorrelated noise, we only see a 12% increase in the residual. It's very fast. Using GPU acceleration, it only takes 5 milliseconds to process a donut, and it's accurate. So next slide, please. So thank you so much. I know this was a quick summary. If you're interested in the details of these techniques, you can check out our 2 papers shown here. And if you have any questions, feel free to ask in the chat or email me. Thank you.
Thank you, David. And thank you to all the speakers for keeping to time. We managed to get through all of the talks in the right amount of time. We are going to go to questions. We're formally at the end of the actual session of the hour long, but we'll keep going for a few minutes to address any questions. I know that many questions for Josh were answered in the actual Slack. So if you want to ask questions, please raise your hand. Otherwise, I'll go to Bo, who had a question for David about slide 76, and I will bring that slide up.
Yeah, I was just interested in learning more about how this particular plot was produced, like how exactly is the wavefront power defined, for example?
Sure. So what we're doing here is we take those 500 full observations, and the way we choose the range in which to perturb the telescope is for each individual degree of freedom, with kind of the standard 50 degrees of freedom for Rubin, kind of the 10 hard points and 40 bending modes, I think. your team uses. We see how much we'd have to shift it in order to have a 0.3 RMS in wavelength error, and then to draw perturbations for across all these parameters. We basically set it up so that you have 5 times the amount of error that on any one of these would lead to 0.3 wavefront error RMS. So that's how we choose the range. Mm-hmm. And then how are we measuring this? So it's we get these 54 or a more extended set of global wavefront coefficients, and we sum up their component-wise absolute values, and then we see how much of that is captured in the first 3, if we only use the first 3 focal plane indexes.
Okay, so maybe it's related. So how are your input images perturbed? I mean, when you generate those images, do you only perturb the system in terms of the 54 double zero-nities?
Only in terms of those 50 degrees of freedom.
Oh, you perturb the degrees of freedom. Okay.
Yeah.
Okay, thank you.
Sure.
Then Nevin had a question for Josh about only one defocused image.
Yeah, Josh, I don't know if you saw, maybe we talked about it, but basically I didn't fully understand how is the different, you said 2 images before, and now I need only 1. How is that different? I would assume that the method would be basically agnostic to
that. I think I can answer maybe the second part of your question, which is the wavefront does not change with defocus. So the way I've been thinking about this in practice is to actually measure the perturbation from the design wavefront. And so you know what the design wavefront is, both in focus and out of focus. And as long as the perturbation is what you're measuring, it's not a problem.
Sounds great. I was just confused for a second. All right.
Okay, and then Chris, you have a question for David about the simulated fidelity.
Right. I was just curious, and it was very interesting. You made a large simulated data set. Have you tried to do any tests where you take the result of the trained network and put some sort of systematic errors, differences in where the real data would look different than your simulated training data set, and see how robust the results are to those kinds of perturbations?
We haven't. That's a great suggestion. And interestingly, I think a lot of methods for wavefront sensing that are being explored for Rubin, they all kind of have this problem that they're tied to simulation results. But yeah, what you suggested would be a great thing to do.
Great, thanks.
And then I actually had a question for Aaron, and that was on your slide 54, where you're doing the comparison between the AOS and the PSF. Do you have a sense of where you talk about this, the offset in this stigmatism? Do you understand where the offsets are coming from?
One, the source that I'm concerned about is what I call the set point, right? So any feedback system, you have to define where you're driving it to, your set point. So what does 0 mean? And the 0 may be systematically offset. And so it is possible the procedure I described, well, I didn't describe it, I mentioned it, of stitching the in-focus and out-of-focus wavefronts, that might have been imperfect. I did it a long time ago, actually, when I think I understood less of what was going on in DECAM. And so it's possible that just had an error in it, or had some systematic effect in it. But you would see it in kind of this, not going through 0, 0. Does that answer your question?
Yeah, that's great. Thanks. And then Aaron, you had a follow-up question for someone else, right?
Oh, actually, I was just going to follow up Chris Walter's comment, which is in particular, and it's it's because of this fine order structure that you see in donuts that both I mentioned and Nevin talked about. Josh has talked about it from Hyperspectral Chem imaging too. You know, that's due to mirror figure errors. And so that is a really good source of differences between data and model that are worth exploring in any picture. And you know, we do have measurements of the M1, M3, and M2 surfaces. And so simulating those surfaces, I think, would be very interesting.
Okay, thank you. And then Keith, you have a question for Bo about the status of the optical feedback controller.
Yeah, I think this is a question for Bo. If you could just say a little bit more about the controller, basically how you do this translation between the wavefront that's been measured and the forces that actually get applied, and how that gets trained up.
Okay, so to the first order, well, you have a state estimator, then a controller. So using your wavefront estimates, you estimate the system state. Then based on your control logic, you decide how you can best correct that disturbed system state. So we define a cost function, which has two terms. One is the one characterizes the image quality, the other is about control motions. We want a balanced control system. You don't want to have large swings in your control motion to make really small gains in image quality. So without going into too much detail, I think that's probably the best way to summarize how the AOS control works. Then in terms of the status, so we have like a toolbox, we have different tools, different knobs, basically different parameters we can further fine tune. Those are all in place already, implemented in the software. So the plan is we're gonna run more simulations so that we can learn more about how we can better fine tune these parameters and which control strategy works best in work scenario. Then of course, eventually when we go on sky with commissioning data, we're gonna go through that exercise again.
Is this something that can be measured at all before going on sky with actual, I'll call it data, but what I mean to say is sort of not simulation based, but somehow like testing the mechanical feedback loop? Or does that really require on sky data?
In terms of making the algorithms really work, I think we will need on sky data because no other existing telescopes will give us similar characteristics as the real LSST. So, but again, we are doing our best to use simulated data to learn as much as possible from this data, see how we can best speed up the process when we have the actual data. And meanwhile, well, that's for the algorithm itself. On the other hand, as you saw from one of my slides, we are doing what we call this level 3 testing. So these are using the actual hardware, but yeah, that's mostly interface kind of verification testing, which is not really testing the algorithms, I would say. But it's also an important part of making sure it will work.
Thanks, that helps.
Great. I think there's a couple of SPIE papers as well that explain kind of the system in a little bit more detail as well. Maybe we could post some of those to the Slack channel. So we are at time, or a little bit over time. I want to thank all of the speakers again for the wide-ranging set of talks. In terms of the AOS group, I know that we'll be following up with multiple of the talks to learn a bit more of this in detail, and also that we and we'll likely kind of come back to these in more detail when we do our regular in-person meetings for the AOS system. So thank you all, and we will end this session.